Hey guys, this is Carrie, and in this video we're going to be doing the answer key for homework number 1. So let's take a look at the first problem. What is the fundamental theorem of algebra? So what the fundamental theorem of algebra states is the highest exponent in a polynomial equation will tell you the number of solutions the equation has. And so we see that really relevant in the conversation that we're having in this unit when we look at an equation like x squared equals -1. So an example of the fundamental theorem is we would expect this equation to have two solutions. And part of the motivation for introducing this new number I is that when you go to solve it, if I doesn't exist, you actually find that because you have the square root of a negative, it would actually lead you to believe you have no solutions. But that's like the motivating factor in introducing I, is that it allows you to have the right number of solutions, two solutions to this equation. So speaking a little bit about I, what is the meaning of I in mathematics? You could answer this in a variety of ways. One way you could answer it is you could actually say that I is equal to, what combination of numbers and operations is I equal to? It's equal to the square root of -1. And this is the mathematical definition of I. So what I stands for is the imaginary number, which we learned in class. Originally, this was a name used to kind of like be condescending towards this number. So it was Rene Descartes who started calling it the imaginary number. And what he meant was that this number couldn't possibly exist, because how can you find the square root of a negative? However, the name stuck, imaginary number, and even though today it's very useful in a variety of different ways, unfortunately we still call it the imaginary number. It's one of the great misnomers in math. Determine the value of root -64 in terms of I. So one of the really nice parts about I is that you might think you would need a new number for all of the square roots of negatives, but you actually only need I. So if you write square root of -64 as square root of -1 times 64, then when you're evaluating this, you can do the square root separately. The square root of 64, let's just a plain number because we took care of the negative separately, is 8. And the square root of -1, that is our definition of I, so we get 8I. And we're done. All right, so let's see, for problem 4, this is a really good job of illustrating where the fundamental theorem of algebra connects to this new number. So we have x squared equals -36. We're expecting two solutions. So to obtain those solutions, we take the square root of both sides. When you square root to cancel square, you get the positive and negative solution. Now, square root of -36, before today, before yesterday, whenever you learned I, it didn't exist. We had no solutions. But you can evaluate this by thinking about it as I times, -1 times 36, and then each of these can be done separately. So you get x equals, square root of 36 is 6, square root of -1 is I. But you also have the plus or minus in front, so you have plus or minus 6I. And you might say, well, that looks like one solution, but remember, plus or minus, what it means is you've got positive 6I or negative 6I. That's from the plus or minus. There's your two solutions. So fundamental theorem of algebra still works. Solve the equation x squared minus 10x equals -34 for all values of x. Your first instinct might be, well, I'll add 34 on both sides. This turns it into a sum and product problem. But unfortunately, the only pairs of numbers I can think of that multiply to 34 are 34 and 1, which don't sum to 10. Sorry, I'll write it like this, 34 and 1, which don't sum to -10. Or 17 and 2, which sum to 19 and not 10. So because no combination of numbers will add to -10 and multiply to 34, this is not the correct route. So actually, I'm going to erase it back to the beginning. All right, so maybe a better instinct for solving this would be, instead of moving the 34 over here, let's put a better number here. So the number that I want there is 25. I'm using the method of completing the square. because we want the 25 there, let's see what that gives us. When we do this, we get x squared minus 10x plus 25 equals negative 9. This is now a perfect square trinomial. We get x minus 5 times itself equals negative 9. And this equation now, because we have a single x, can just be isolated using inverse operations. So we'll take the square root of both sides. Ooh, I missed something. Include the negative underneath the square root, right? Square roots cancel squares, and that gives us two solutions. We get x minus 5 equals plus or minus the square root of negative 9. Before this, we would say the square root of negative 9 does not exist, and that would mean we had no solution. But of course, now that we have I, we can do this. So we get x minus 5 equals plus or minus the square root of negative 1 times 9. X minus 5 equals plus or minus square root of 9 is 3. Square root of negative 1 is I. Add 5 on both sides, and we get x equals 5 plus or minus 3i. Whoa. Well, you're right, complex numbers. So complex numbers are numbers that have a real part and imaginary part. I'll write that. This is called a complex number. You'll always write the real part first, followed by the imaginary part. Determine the value of square root negative 9 over 4 in terms of I. Oh man, this one looks crazy, but actually, square roots of fractions are pretty easy. To do the square root of negative 9 over 4, we saw in our square root unit that this is the same thing as square root of negative 9 divided by square root of 4, doing them each separately. Square root of negative 9 is 3i, square root of 4 is 2. This equals 3i over 2. Determine the value of square root negative 45 in terms of I. Square root negative 45, oh man. Well, we know we can break that down into the square root of negative 1 times 45, but the major difference between this problem and any other problem that we've seen so far is the square root of 45 isn't so nice. So we actually have to break 45 down further. So I'm going to leave the negative 1 separate, and I'll treat 45 off to the side. That's 5 and 9, that's 3 and 3. So this gives us negative 1 times 5 times 3 times 3. Now when we're evaluating the square root of negative 1 is I. The square root of 3 times 3, well, we can use the jailbreak method. 1 gets out, 1 dies, we get 3i. And then still left in jail, we've got the square root of 5. So we have a strange looking, sort of irrational, imaginary combination here, but that's fine.